Welcome back to part 2 of the slime tool. In this part I will be focusing on adding simulation to our static organic slime mesh, and after that we'll look at how to actually create a mesh from that. So first, for the simulation we want our rest length, and we can get rest length. This is so that the simulation knows what length our line were before the simulation. Next you want a wrangle, and we want to just first set some visualization for our group. We have our on surface points, and let's check which points are in there and just set them to green, and else set them to red. So you can see that our on surface points are perfect to pin our simulation from. So next we want to set our p-scale to some value. Like, we basically need a p-scale for the vellum sim, and we want to just have a pretty small value. And the most important is our thickness. So we basically want to power our gradient attribute, which was a value that went from 1 to 0 to 1 over our curve. We want to scale this, and we want to add a bias. This to 0.5, this to 2, scale, and a bias of 0.3. So the reason we have a bias is we're going to scale our stiffness with this stiffness value, and we don't want a stiffness of 0. It will make the sim go crazy, because stiffness of 0 will just make them stretch and bend indefinitely. And with a power if we actually press I, can visualize our stiffness. And with the power we can control the fall off of our stiffness, so we can make the middle is sort of the droopiest, like this is pinned, so it would look weird if these parts were completely not stiff. So we need this fall off, probably keep it at 2. Our bias is sort of the minimum stiffness in this middle, and I think 0.3 is a good value. We can scale it, but just leave it at 1 for now. So next is the vellum constraints, and we can use our on-surface attribute as a pin. So we just say pin to target, pin the points in the on-surface group. And then another vellum constraint, which will tell vellum that we're working with a string, can leave everything at default except for the stiffness in the stretch scale by attribute, stiffness, and our bend scale by attribute, stiffness. Then next is a vellum solver. And we can see that we have an animation now. And we can play with these scalars. So we might want to make it more stiff in the bend. And maybe we want to make it less stiff in the stretch, that we can stretch it out a little more. Okay, and after that we want a time shift. What are you complaining about? Okay, let's recycle that vellum solver. It's probably because I connected it to itself. So we use a time shift here because we will use that later to control the amount of simulating that we're doing. Because in Unreal with our HCA, we won't have a timeline. We won't be able to press play for a simulation. We'll only be able to set attributes, but we'll still cook the network. So by controlling this frame number, and we'll use Python scripts for that because it doesn't work as an attribute out of the box, I control at what frame we will be in our simulation. So next we want to start working on our secondary simulation. So we've used this like with a pretty high snap distance. And then we want to wrangle, and we want to select certain points that we're not going to use. So if a random of our ptnum is higher than drip amount, remove point. So if we have 0 drips, we get no points, and we can, blah, blah, simple. Then we want to scale our p-scale with a minimum value as the base, and we'll add to that the random point number minus or times our max minus our min. So max value of 1, max value of 0.1. So we have 0.1 as the basis, and then we get the difference between our min and max, which will be 0.9, multiplied by the random value of 0 to 1. So at max we'll get 0.9. So we have the minimum, and then at max we get plus 0.9, which equals the 1. And then we have our p-scale. want to have a couple of points. You want to have a simple sphere. Just set it to polygon and one frequency. I want to copy that to our drip points. Then from this, we want to create a group on our base mesh. I want to say that the point group, call it resim, no base group, keep in bounding object. And now we have all the points that were selected by our drips. Then I want to say do a group expand of our resim group, call it resim expanded. Can blast the resim expanded, delete non-selected. And here we have our points, lines that we want to use for the secondary sim. So again, we place down a wrangle. First, we subdivide this. We basically have a smaller scale simulation, but we're still working with the same resolution of our base sim. So we want to have a little bit more points to work with. Then we want to set attributes, and we can just go up to this node. Basically copy all this. Instead of our on surface group, let's check our resim. We can see that we have these small edges because we expanded this resim. So we can use that as our pin group. So we can basically just copy this setup. Don't forget to set our attributes. Point scale, power to 2, scale to 1, this 2.3. Then in here, instead of on surface, we don't want resim because that's the part that we are simulating, but we won't want resim expanded either, but we can just do everything but resim because that's everything that's left. So that's our pin group. Our string group works the same. I probably want less stretch because we want these to start falling down. And we can already see that they are going down nicely, but it could be even less. You can't go too far because otherwise this happens. Put less in the bend. Maybe even lower. And then after that we place a time shift node. Delete channels, put it to frame 30 or something. And then merge it back with our original simulation. Okay. And if you still know, we did have our world geometry. So we can actually copy this object merge, bring it down, and we can plug it in our collider. So if we now resim this, then we can see that they are nicely falling on the ground. Merge this, put on a null, call it out simulation. Okay, before we continue, let's create some attributes on our HCA. To work on this a little bit. First, I want to create an ordered menu. And we call this mode. And the first token and label will be edit. The second one will be simulation. And the third one will be mesh. So this is the different modes that our user can switch through. So it will use the edit mode to edit the position of the curves and general composition of everything. And in the simulation mode, we can tweak all the values for the simulation and sort of how much we want it hanging, etc. And then the third one, we can finally generate the mesh and have sort of the most expensive part of the process be the last part when everything is set in stone. So drag our seed up and we need to make some folders like so. And for our editing, we want to have the surface gen, surface this, and the width and the lines. Our seed is something that keep at the top. By the way, we can add a seed parameter to our set drip randomization. Parameters, get our seed and paste it there. Our drip and size needs to be in the simulation. Then I want button. So one button we want to call drip min. We just want it labeled with the negative sign. And then we want a drip plus. We need an integer for the drip sim frame. So we will have a plus and min button for the simulation frame, which will edit this frame. why we don't just set this parameters if we sort of skip ahead or we try to change this with more than one frame at a time, which we actually don't want our users to do. So we give them these buttons so they can sort of go back and forth one frame at a time. That way the simulation won't break. Then we have the same for like sim min plus. These. I probably already had these created, but we just created three floats for the drip amount, the drip size, and the max drip size. And yeah, we need to connect them to these parameters. So drip amount, min, and max. Did we already hook up our edit stuff? Yes. So while we're at it, let's just continue with the creation of the parameters. So for our mesh, we're gonna need float, and this will be, but we already have a width string. We want to give control to the polyreduce, reduce to, so the player can have a say in how intense they want to optimize the mesh. And then last but not least, we want two strings. One will be the material and the other will be the decal. You can decide for yourself how much you want to expose to the user. Like you might just want to give a regular drip size and you just calculate a min and max drip size based on that. So we just create a drip size and we actually remove the max drip. And then in here, and then we see if the drip size is 1, then the minimum drip size is 30% of that, like that. And we have drip amount, drip size, and let's call this thickness. Let's do that. All right, then there is one more thing to do, and that's the writing the code to set these parameters based on the button presses. And for that, we first need to go into the scripts and we need to create a Python module. And here we need to define some functions. Yes, let's get our nodes. So we have our, let's call it Vellum1. And this is our Vellum solver 1, which is the name of our first Vellum node. And we need to get this node because what we want to do is if we switch the mode, this is the function that we will call whenever the user changes this parameter. If that happens, we actually want to resimulate the simulations because otherwise they will sort of start hanging and everything just needs to be freshed whenever the user is changing modes. And you can press the button by doing nparm and have the resimulate. Reset simulation is called resimulate. If a pop-up doesn't appear, you can just go into its type properties and find. So we press that button whenever this gets called, and I need to stay in the v1, and then v1.cook true, and this will sort of reset this node whenever mode is set. So we want to do the same for our v2, and this is our Vellum solver 2, this one, just the same code. We have a sim min function. This will happen when we press our negative sign on like the buttons. We need to get our sim frame attribute because we want to edit that. And then you can say parm is node.parm sim frame. And I'm going to set a value parm.eval are getting the current value and we're subtracting 1. And then we can do set val because we want to, whenever the button is pressed, we want to get this value from this parm, subtract 1 and set it to that. Then we can do the same for the plus version, but then we add 1. And we need to do the same for drip min. And let's see, drip sim frame, that's what it was. And now I want to make sure, like we have now these functions saved in our Python module script. And if we go to the parameters, we have these callback scripts, which we'll use to call the right function on these. The way you do this is use the quarks, which sort of gets the information on this node. We want to go into an Houdini module and we want to say sim minus and then pass in the quark and the node like so. If we now set this to 4, we press this, we go down because it executes the script. So we can copy our quarks node, Houdini module, sim min quarks node, get it in here, but then just do the plus. And this is just the name that we gave it here. We're just gonna copy paste this everywhere. Drip min. And then on this one, we want to get our mode. Now let's test. Okay, and the user can still do this. Like maybe it will get fixed in a later version that we can just scrub through this and set it like that. But for now, I found that this is the only way that you can control the simulation frame from within Unreal Engine. Okay, let's start with meshing our lines. First, you want to get a for each connected piece. So you want to utilize the way that everything is still disconnected from our simulation pass, because I want to give these hanging parts a different thickness than the other parts of the line. Like I want to make sure that it really looks like they dripped down because they gathered more slime, more weight, so they sort of fell down due to gravity. So it checks if they're connected and then we'll loop over them and we will measure. We can use the bounding box or we can use the color maybe. But for now I'm going to use the bounds because that's just sort of respective to how gravity works, like higher points are higher. So we get bbox max, which will just get the maximum value, the maximum vector value of our bounding box, and we get the min. And then we get y size is the absolute of maximum of y minus the minimum of y. This is if we are dealing with negative values. Size relative is the maximum y minus the position in y. And then our size is, it's just size rel divided by size. And if we visualize this, you can see that we have gradients on all our hanging parts. So where that went that, we want to fuse that with something nearly small but not too big. So that now everything is snapped, nothing is loose again. We want to get a wrangle and we call this wrangle thickness. And we have 3 colors. We have 3 separate ways of making our thickness. So first we need float R, and this R will be our overall width divided by 2, sort of like a radius of the thickness of the slime. Then we need a max points and set this to something like 600. Then we're gonna check our nearing points. We want to cast this to float. We want to get a length of whatever the PCFind function will find for us. Max points. And while we're casting this to a float, we're gonna divide it by the max point so that we get a value from 0 to 1. And they're both floats, so it won't give us a float back, or we'll just return 0. And then we can get our base thickness, and again, get our thickness from here, paste relative reference. Then I want to say, okay, if our color is red, so if CDR is higher than 0.9, thickness, pluses, general ramp, size, nice. This will just be a ramp that goes something like this. Maybe go to 0.5. And I will control the thickness of the red part. We can maybe already put down a sweep and we can say FFP scale is thickness. Set this to round tube. Don't apply. Now you can see that where there are more points together, that will get thicker. And maybe we can just say if it's higher than 0.5 because or higher than 0.1. If color green is higher than 0.1, we just want to multiply it by 9 or something. Close that. And if blue is higher than 0.1, we want to say thickness plus is channel ramp drips with our size, wrong brackets, make this B spline. And let's put this to something like 2, and let's put this down like so. So now you can see that the blue parts, they're thin here, and then they sort of blob around the bottom. Some of them turn into amazing discs, but probably because this is just way too intense. Yeah. And we could maybe just multiply equals these things. Maybe put this to 3, and maybe put this to 0.1. Let's keep it at 0, just add 1 to each. So now our user can use the thickness to sort of scale everything, and this will just be a ramp that we can set, but the user doesn't, or the end user don't have to touch this. And we can maybe lower this to 300 so we get more thicker areas. Let's put it at 0.1, like that. We put it at 4 times as big. Yep. So now we can add an attribute noise. I want to noise up our p-scale. We want to add it to float. Play with the element size. Just added like a general noise to our thickness. And then to sort of counteract these weird spikes, we can blur it. Oh, and also in our sweep nodes, we want to get some end caps. Blur on proximity. You know what? Skip the blur. And maybe before this, we can use an orient along curve. So now what we want to do is we want to move these points that are along the surface. We want to move them across the surface so that we sort of get this nice fall off, that it really looks like it's sort of, or it really latched onto it. And we need normals for that. We also need our world. We need to promote our vertex normals primitives. And we need to get our point primitives here, and we need a wrangle and call it expand along surface. We want to get an integer for storing the primitive value. We need the primitive UV because we need to pass it into the XYZ distance function, which will get the closest primitive to our position. And then from that we can get the primitive normal, the prim function, and our prim that we got. Then we can cross this with our point normal, and this will get us a vector that is perpendicular to the normal and the other normal. So for example, if we here have our normal that's pointing that way and the surface normal is in this case pointing that way, then we get sort of a sideways vector here. It's coming towards the camera, but we actually want our somewhere in the direction of our original normal, but we don't want to use our normals because our normals are kind of weird oriented like that. We only use this normal to get this. So we cross these vectors again, and then we get a vector that is aligned against our surface normal. So we get our offset normal, and then we say if our green color is bigger than 0.1, and if the XYZ is smaller than our distance, we say the position plus equals the offset times a strength. Nothing is happening. And that's because we have an M here instead of an N. Let's go. And as you can see, we're now offsetting this. And now you question, could we just use the normal? The normal is somewhat pointing, but we have a lot of normals that are actually not, like in a way we are projecting the normal back onto the normal of the rolled surface. Because we use the surface normal twice, we make sure that it is aligned with that vector, or it is aligned with the perpendicular plane of that vector, which is like on the surface of that primitive. So I want to switch this back to offset, and then we're good to go. So now we can get into the VDB from polygons, and we use a voxel size, which is 0.5 times our thickness, which we need to get from here. Because our thickness is sort of the minimum thickness that our user wants. So we divide it by half so that we have 2 voxels per the thickness that we have. So it doesn't become a beautiful volume, but it is a fast volume. Right off the bat, we can convert VDB back into polygons. And then what we want to do in this stage, we want to do the Boolean with our surface objects, and then we can cut this off. And now you can see that we are sort of benefiting from this expand along surface. Like if we put this to 0, we really have these like harsh fall-offs, and when we put it to 0.5, we get this nice smooth attachments to our ceiling. And we might even put this lower. Now we also get open. So here's our polyreduce. I'm gonna smooth it out a little, delete attributes. And now we want to transfer from attributes, and we want to get the attributes from these points. And we want to get our beautiful color back from points to points. Some samples and then blur it. Just with 3 should be enough. We can identify our stuff. So what we're gonna do next is we're gonna prepare our vertex colors for shading. And first we're gonna scale our blue color, and we wanna scale it based on the distance from our curve, the input curve, or like not the actual input, but the one we resampled. Wanna subdivide it a little bit and then grab it. We wanna do something else with the curve later. But first, let's edit our color B, and let's multiply it with the XYZ distance from our line. So now points close to the line will get darker, and we really get this nice fall off in our blue color. And we want to do some measuring, curvature, thickness, and promote. We want to promote our color from point to detail, and because we can then get the maximum. I don't want to delete the original. In our measure curvature, we just want to get these values. We don't really want to adjust any of it. Or the default should be good. Let's visualize our thickness first. This is sort of a volume operation. And we actually want the max thickness to be similar to the thickness we've set here. But remember that we scaled it in this node with 4 for the green channel. And we actually just want to do that the same here, so that our maximum thickness is the maximum that we sort of assigned. And then in this node, we're going to set the vertex colors. We need a success int for that, because we're going to use a dthrow attribute function. We're going to get our max color like that. And then we will divide our color blue by the max color, so that we were multiplying it by a distance which can be anything really. So we need to normalize it. Now we check if our RNG together is higher than 0.3, which will be for most points except for the ones that were blue. And we want to just make sure that these don't have any blue color, because we're going to use the blue color in the shader for something that's specific to the hanging drips. So this is just like a safety check. And then we want to set our color R to our thickness, and our color green to our curvature. And we can use convexity or concavity. Doesn't really matter because they're the opposite anyway. So if you want the other mask, you just invert it. Oh, we have it in the wrong inputs. Let's go. Let's try some different settings here, because this one is not working. Like, this is getting good values. I'm gonna use that so we can more just distinguish like these connection points from the lines. I also maybe want to go back and change the thickness of the red part a little bit. Yes, let's just lower this to 0.1, because these can become very, or they're allowed to become very narrow. I can remove all this and keep it to a nice curve like that. We have our vertex color. Our curvature is fucked up again. Let's use it from the measure sub. I think that will be most consistent. We want to split this into 3 different groups. And we actually only want 2 of these. And let's get this into a group. And these will be our LODs. So you can just make a primitive group and call it LOD0. And Unreal will detect this as our different LOD levels. So just for no reason, we create 3 LODs. You create how much you would need for your game. And this is also just dependent on what you would want, but generally speaking, you want something to be half and then just 20%. Like, you don't want to push it too far, because then everything breaks. Let's do 10%, and let's do 30. In this polyreduce, something I forgot, we can get our percent to reduce to, and we can set that here. So this is a way the user sort of has control over all the, because if they reduce this, they will also reduce the LODs. But this is sort of like if you have one of LOD, and you can of course change, you could also expose it if you want, but whatever. We're gonna just merge these together and have all our LODs at the same time. Then we want to set our Unreal material as at Unreal underscore material. Unreal will automatically get the material that this path is set to. So if we expose this, and if we then get our beautiful parameter here and paste relative reference, then the user can just drag and drop materials on this slot in the HTA editor, and it will automatically paste the path. That path gets then automatically assigned on the geometry, and then we have our material instantly applied to our slime. Then I like to have soft normals. Put this in a final group that's called geo, and this will tell Unreal that this is our actual geometry, our display geometry. And then on the right here, we want to create our collider meshes. So we're going to resample our curve again, and we're going to resample it with a length of 3. And we're going to need our tangent attribute as our normal. Gonna make a group points, call it cuts, group expand, and let's just keep the same name and do -1. So what this is doing, well, we only get 3 points here, but if we have just 3 points, we actually just want 1. We don't want the edge points because we don't want to be cutting there. For this one, we basically just want to cut it in half and have 2 sides to work on. If it's longer, then we will have maybe 2 like this, and we have a middle piece, 2 on these sides. Like we can't make perfect colliders for this, of course, but we can do our best, and we're gonna get pretty close. So we're gonna blast everything that is not a cut, which will just leave us with the center points for this, and then we're gonna place a grid, and this grid will be definitely squared. And then let's just take our overall width and multiply that by 10, and we just need to copy 2 points. So we want this in the X and Y plane so that it's oriented along our point normal. Then we can do the boolean, a boolean, the main boolean that will cut up our geometry. We want to say this is a surface, and this is also a surface because it is not watertight. We just want to shatter it. Then we can say delete small parts. And this is just more of a safety, but it's also some parts that would be too small. You could just exclude them. Unfortunately, I did not find out a way to cut off pieces like this, but hey, maybe you can find it out. Then we say for each connected piece again, which will give us 2 pieces for this. And then we just say convex hull. We create a convex hull, but this isn't really good geometry yet for collisions, so we need to polyreduce it. The way I found best is to just get an output polygon count and put this to at maximum 16, because then you have sort of the most shape-ish still, but you won't get these like crazy convex hull thingies, and that will also make sort of double lines here. But if we just say, well, you just have 16 polygons to work with, do it with that, then we will get pretty nice collision geometry. Place this in a group, and our group has to be called collision geo UCX. Then we merged it and we put it in a null. This is our mesh. And then we have our other switch, and we can get in our mode like that. And I see that I forgot while doing all this that we still need to create our export for our edit mode, which is kind of easy. We just take the point where we get our thickness, because this part is still quite fast to calculate. We don't want this sweep because we want to get like the fastest and most performance sweep that we can make. So we get this, we fuse it, and then we, well, first we fuse it, but we also want to fuse it with a pretty big snap distance, like 1/4 of the width or something like that. Then we want to sweep this with just 3 columns, and we basically want to turn everything off that we can. So also in construction, we don't need this. We need anything. We just wanted to make some geometry. And that will look like this. Like it will be connected at every segment. Like this is the fastest and cheapest way to create some volume around it. And it's kind of the same as we did here, but now we have our simulation shapes into it. Next is an attribute promote to promote our color to primitive so that we have even less data. And then we do a group delete, so we just delete all the groups, and an attribute delete where we delete everything except the color. And this will be our simulation output, that's like that. And then our modes, we still need to set that. This copy, paste. Then we can go up and adjust the lines. You can say, hey, we want to be in simulation. You see it's recooks. And we can say simulate it further. Oh, we need to still copy these in our time shifts. So this is the main one, sim frame. And then we have drip sim frame, which is 6. And now we can say simulate it, and here we can also, and we can sort of pick whatever frame you want. I guess we can also do this, see if it still holds up in Unreal. And let's check if we can get our drip amount. Okay, so there's still something that we need to do. In our scripts, we need to add another definition for reset. We need Vellum Solver 2. We basically just want this, but in a separate function. And whenever the drip amounts are changed, we basically want to call this reset function. Why? Well, because if we change the drip amount, we need the sim to reset. Let's see if the drip amount is connected correctly. Nope. And then as last test, we can go in our mesh, and you can see it takes increasingly longer, of course. And here we have our multiple meshes stacked on top of each other. We can use a blast to just get LED 0. And here's our base mesh. Okay, so one last thing, I've really left this on single pass, and you could actually experiment with this resample. Like if we disable this, we actually get a way better LEDs. Like you have a lot more LED meshes, but I think for something complex like this, if you need more accurate LEDs, you can just disable this resample or add more segments in this resample. But you can see that it cuts it nicely along the lines, and you get these middle smaller chunks, so you actually have no collision here. Like if we kept it enabled, then it was just one big chunk. And then at the end here, we want to set some final Unreal parameters. So there's an integer called Unreal U property, override global proxy static mesh settings equals to 1. And then Unreal property distance field resolution scale is 0. We don't really want to calculate distance fields for this. And we want enable proxy static mesh to 1. So proxy static mesh is something that is kind of new since Houdini engine 2.0, if I'm correct. But this will make your mesh a proxy mesh, and it will generate it a lot quicker than if it was just a real mesh. And at the end of, like, if your user is done setting all the settings and they have a result that they want, then they can bake down the mesh and then they get the actual mesh. But if you don't set this parameter, then it will just keep generating the other normal mesh, which is a lot slower. And we really need every little bit of speed with this tool. So we can call this set Unreal drips, and that is it for this video. And I'll see you in the next one where we go into Unreal and do the final shader setup.